Hello and welcome to a bonus presentation, so to speak. Some things that don't necessarily fit in well with the modules as we go through them, module 2 and 3 and so on, but kind of are thematic in nature, right, that span multiple modules and things to talk about. And today I thought I'd run through the best practices related to Python development, and some of this I'll spread into also into R. But we'll go ahead and jump straight in. So there are lots of different ways to develop code. The basic idea here is to present some of the concepts, themes that might not show up otherwise. It's around being able to kind of leverage software engineering skills and so on in the domain of data science. So go ahead and jump straight in. We'll talk a little bit about error handling and logging. The concept of separation of concerns, and then some acronyms. Along the way, we'll take a look at some logging examples. So error handling and logging, important stuff because things happen. You're dealing with interpreted languages whenever you're dealing with Python, R, and most of the courses, or most of the languages you'll deal with during a data science curriculum. Most things don't have a compiler. Compilers are nice in that they sometimes can catch errors, syntactic errors and whatever else. They're in compile time versus at runtime. Because you're running with something that's interpreted, you're going to have runtime errors. They will generally occur. The thing is to be able to handle them appropriately, either to potentially avoid them or at least capture enough information so that you can address them whenever you encounter them. So if something happens, you need to know that it happened. That's a key concept, especially whenever you move past experimentation into productization of your implementation, so that they are running in a real world situation, potentially at scale. It's really important that if it sees something, your model or your data processing pipeline or whatever it might be, if it sees something you haven't seen before and doesn't handle it well, you've got to have something in place to help you diagnose those sort of situations. One of the things I've talked a little bit about is to use assertions. Assertions are important for two or three reasons. One, they can help you programmatically state what you think things should be. So it's a way of about your expectations of things. So if you implemented code in a certain way, thinking that it should be structured a certain way, have a certain value present, shouldn't have a certain value present, whatever those things might be, then an assertion is a good way to do that. It's a way of checking to see if things are not null that you feel that should be null, and so on. Generally speaking, the result of an assertion that is not going to be true is it's going to throw an exception, which is exactly what should be done, because things are not what you expect them to be. And this is also a guiding principle for you. Because they're not what you want them to be, then you shouldn't attempt to continue processing, because something is clearly bad that's going to happen, right? So that's one thing. The second part of the reason why assertions are really important for any kind of development is that they capture what the person who implemented a piece of code was thinking as they implemented it. So it's a way of more strongly, rather than just in a comment, it's a way of basically saying, this is what I think the world should look like from this perspective whenever my code is running. So with that in mind, they are really important. So they do multiple things, multiple reasons why you should do them. It does make sense. If there is something that you expect to be the case and you can think that it is something, then you should use an assertion. Value substitution kind of corresponds somewhat with assertions, but more so whenever you're dealing with either missing values or bad values, you have choices you have to make about what you should do in those situations. So an example might be a data set might have a column that occasionally has a missing value in it. Your choices are, you could potentially exclude the row. That is one possible choice. Maybe the right choice may not be. A lot of these things are situational, right? So it kind of depends. If you're dealing with, say, a pressure reading and you have readings on both sides of a missing value, you could potentially put the average in. That is a reasonable expectation of things to do. But you need to be very cautious with this sort of approach, because it could be that that value is missing because the sensor went offline, hinting at maybe a fault of some sort. So it is something that has to be done with a lot of care, but you do sometimes do things like put in a reasonable value in place of a missing value or an erroneous value. But you may also want to keep track of the fact that you did so in case, right? So that it is clear that you did do a fix-up or a modification or a smoothing or something to that particular record along the way. Another thing I've talked a bit about before is to use try and except inside of your code. There are some sort of broad rules or guidelines is probably a better word that you should keep in mind whenever you're dealing with things like exception handling. You shouldn't catch something if you don't know what to do if you catch it, right? That's a kind of a common sense thing to say, but you definitely don't want to catch everything and basically make it go away by not rethrowing it or re-raising it. So that is, some people will do that as a way of having, no errors in their code. They might essentially stop, catch them all and basically just keep processing. So ignoring the error conditions. Probably not a great plan. At very least, if you catch an exception and it truly is an exception, meaning it is something outside of the realm of possibility that you as the developer foresaw, and it's not something that's easy to handle and deal with, at very least you should attempt to continue, if you can, logging what you did, and we'll talk about logging in a moment. I guess one of the key things here is, as I've talked in the past, don't use exceptions as a use of flow control, mainly because your performance will be horrible. There is, however, to kind of contrast with that, a design philosophy, especially in Python, that basically is a minimalist approach of write code that should work most of the time and then worry about the cases that don't later on. You kind of have to strike a balance between those two extremes, right? You can't just be blindly assuming that everything's going to work, and if it doesn't, throw up your hands and it blows up, right? That's not a good solution. Also, you can't write code, well, you could, but it would take a while to do it and potentially be not all that great of performance because you are dealing with an interpreted environment here. But that looked for every possible error condition, right? So that checked to see that everything is always exactly what it should be whenever you're doing the processing. So the guidance here is to strike that medium boundary between the two, right? So the land between the further extremes of always catching every or checking for every condition that might result in an exception and never checking for any, somewhere between those 2 points, find kind of the right approach. Error logging is, as I mentioned, important primarily because it allows you to capture something that happened that was interesting in a way that you can then potentially come back and diagnose. And the combination of logging with exception handling is a really important thing to do. So with this, we'll switch over and kind of play with a notebook that has some error or some logging in it to kind of get across what the logging concepts are about. Just to, I'll go ahead and restart and clear my output so that it looks more interesting as we go through. So logging is done by doing import logging. It's built into the language, and that's something that tells you something. It is something that is so common that it's kind of just naturally there. If for some reason it's not, you might have to install it. Highly improbable because it is such a fundamental concept. So you do have this concept of doing an import logging, and then there is something called a logger. The logger is essentially a way of accessing kind of the behaviors of it. We'll deal with it in a moment, but we'll start off with just using the logging. Whenever you do logging, there are essentially 5 different methods that you'll typically use when you're creating a log event, and they are logging.critical, logging.error, logging.warning, logging.info, and logging.debug. As you can tell, those are different levels of severity. And the idea here is that you do have this level of logging that you do. This is called verbosity, is the technical term. And the idea here is that you're able to put a logging instruction that could get noisy, that you may not need all the time, but if you're trying to track something down, it might be important. Do keep in mind, though, whenever you do something and say, I only want to log critical errors or critical things, if you have stuff that is debug, and you turn off something, you may miss something that you need to know. So you kind of, again, If it's, you want enough information so that you can figure out kind of what happened, but if you're really trying to do a diagnostic and figure it out, then you're probably going to want some things in there with debug settings going on. So when we run this is basically setting up the method. So we're creating a function, do some logging, and primarily because I call it several times, and well, that's another best practice, is pull that commonly used code and put it into a function, especially if it doesn't change between uses. And what we're doing here is we're setting the level to not set. So that's essentially kind of a default setting. And what that does then is it's pretty much showing everything. It's printing out the debug, the info, the warn, all the way up to critical. So we see that everything is getting logged at this point, to the console or the output window. You can also log to files. I'll show that in a moment, I believe. But whenever you're dealing with something that's notebook based, such as this, sometimes this is just all you need. Where this gets really powerful is if you embed this inside of functions and various other components that you're using, so that you can determine what happens whenever something interesting occurs. The next thing I'll do here is set it to debug, and that's basically going to be the same thing as not set, right? So when we do logging again, it prints out the exact same thing because not set and debug are kind of the same values. If you set it to info, the behavior's not all that terribly surprising. We don't see the debug information any longer. We're just seeing things that are critical, error, warning, and info. This is a very simple case, but you can imagine if you had a complex program with lots of interesting stuff going on, that you would want to be able to turn down the volume of log messages that you're seeing so that you can focus only on the things that are really relevant. And that's where you basically classify yourself, and this is making you do it by deciding which one of these you're going to call, right? Which one of the methods you're going to call. It helps you figure out what kind of thing is this thing that I'm looking at? How important is it? And when might I might need to see it? And is it okay if it goes away? So if it's something that is debug, you almost never run things like in a production environment at a debug level, primarily because the nature of these things is that it will produce a ton of output, right? So you basically want to have enough information you can tell what's going on, but not so much that it's intractable to track down what's going on, and that you run out of logging storage space and so on. So the next step is we might want to set it to warning. That's the next level up. So we're basically working our way up this table of or down this table of severity, right, of level. So we're working our way through, and then we'll get all the way to the bottom. Or top, depending upon how you want to look at things. So I've set it to the logging level now is warning. That means that whenever we encounter those same functions, we're not going to do anything that is more noisy than warning. Same thing if we go to error, you do it again, and we'll see only critical and error. And then the last thing is if you set it to critical, then you'll only see those things which are critical. So here's another kind of a more advanced topic. I'll go ahead and make sure that Colorama is installed, and it is. So what this is a class I borrowed from this guy's GitHub account. And what it'll do, it's essentially setting up a listener or a handler for logging. And that means that whenever a logging event occurs, it goes through this. And the whole point of it is this basically will do some kind of prettier formatting of the logs, making it a little easier for you to see what's going on. So the last thing this did here, we added the handler, and then I set the logging back to debug. And if we do some logging, we can see that's a whole lot prettier and a whole lot more easy for you to tell what's going on. And it's still showing you the message, but it's also doing some nice stuff like the time that it occurred and the severity of it or the criticality of it, and with color coding, so that it's easy to see that debug's not all that important, all the way up to, dark red on a darker background. You can also do things with string formatting. So in this case, we've got we're doing string substitution. The %s gets substituted by this secondary string. That could also be a variable, which is something to consider. But however, you do want to be cautious with logging variables, because you wouldn't want to log something like passwords, right? Or any kind of PII gets really complicated if you log that. So in general, be very cautious of what goes into your logs unless you do some sort of encryption or basically like format preserving encryption so that you can see roughly what it is. Then the last thing that I'm doing here is I'm removing that handler that I added that does the logging, and you'll see that it should revert back to the previous sort of format. You can also set up things to log to files. I'm not going to show that right here, but it is something that you can do and something you'll often do as well. Moving over to R. So this is an R notebook. You can see up here, where my head is in the picture. So up there, see, R notebook. And you probably could tell that also by the install packages logging. If it's not natively installed, whenever you do your library logging, you'll just do the install.packages and logging. And then we basically include it. And then here I'm going to set up similar to like we did in Python, a function. All it does is do some logging. You make a call to basic config to kind of get things set up in a good way. And then we call log something. And basically here you can see there's a little different granularity. There's no critical. There is, however, a fine and a finest. The others pretty much overlap, warning, info, and debug. So what that kind of tells you is an error is an error, probably error you could think of being as a critical. A warning might be an error that's not so critical. Information, and then debug, and then fine and finest. So similar concept. You set the level using, in this case, the word finest, and it'll basically show everything that we're doing. You also notice that this, by default, does that pretty color coding for you, at least on some of the things, right? So fine and finest it doesn't, but the debug, info, warning, and error it does, which are the ones you're going to use most of the time. Probably when you're running these sort of things in a more production-like environment, you're going to be probably set at info. And if you're really cautious about this, you may have some way of controlling it with a log file or a configuration file setting so that you can switch the configuration without having to go in and actually edit the code. So here we're going to set it to fine, and we can see that finest drops off. We don't see it any longer. Set it to debug, and fine drops off. Info, debug dropped off, and then warn, info dropped off, and then lastly error and warning will drop off. So with that, we've seen logging in both Python and R. Very, very kind of similar in nature, probably because one of them borrowed from the other. And it's also realistically kind of what you need whenever you're doing logging in general anyway. So switching back to our presentation, this you can see is how you would log to a file if you were so inclined. You basically make a call to logging.basicconfig, pass in file name and the level that you want, and it'll start logging to that file. You may end up needing to do something to flush the file at the end, but that's basically how this works. And instead of this coming into the window, it's going to go to that file. So that's essentially how that works. Similar concept, you can do things like set format strings, make it so that it's really pretty as far as the amount of information that's shown, including the level name and the number of what is that, milliseconds or something that is going on. So very powerful sort of stuff. The very last thing here, logging.shutdown, will terminate the logging mechanism. Obviously something to do with caution. Separation of concerns, also an important concept whenever you're dealing with programming. The basic idea here is you should do one thing and one thing well. And that applies not necessarily to you as a person, but your code that you write. So whenever you're writing, say, a class, that class should do one thing and do it very, very well. It should not do everything, and that's where you want to avoid that kitchen sink sort of class concept where you're basically going out and sticking all the cool stuff you got all in one place. Things should be together, and that's where this concept of cohesion comes to play. And they also should be loosely coupled so that there's not a huge amount of dependency between elements in different classes. In general, don't copy paste code. That's bad. It's bad for lots of reasons. Instead, do something called abstraction. You take that code, you pull out the stuff that is common that you have a tendency to want to copy, put it into a shared library or class, and then reuse it in that function in that way. At the very least, put it into a function in an include file that you can include into your main notebook or script, whatever you're doing. But ideally, do use classes if you can. And generally speaking, you cluster together, you pull together those things that go together along typically with the data that they interact with. And it's somewhat of an art, although it is something that with practice you become much better at. And generally speaking, though, make sure your code is kind of doing one thing, at least centered on some concept. If you pick a object-oriented approach and using data, and the data is the thing that you interact with, and you minimize the amount of types of data you're storing, it'll kind of just work out. Some acronyms that you may want to consider. These are things that over the years you may run into. So don't repeat yourself, that's dry, and once and only once, kind of similar concepts to avoid duplication of things. So the basic idea here is that anytime you have more than one instance of a piece of code, that means corrections will need to be made that number of times. And also there's a chance that they will diverge, meaning somebody will take and change it in a slightly different way to accomplish something in one place, not change it in a bunch of other places, so that the code bases essentially diverge over time, making them very hard to fix and maintain. And that's where maintenance becomes much higher whenever you have duplication of code. That's one of the reasons why software engineering metrics consider common and duplicated code in a calculation. And it's potentially going to lead to unreliable code, because over time you may have something that either fails to get fixed, does diverge, and somebody just may frankly forget to update a piece of code, or calling one code and they think they're calling different code. You ain't going to need it. Yagni, basically avoid over-engineering. The simplest thing is most likely going to be the right solution, so you build what you need and no more. That is very challenging. Hence the kind of the little cartoon on the right side of Occam's razor versus Occam's professor, which is do this when two things are possible explanations. The simpler one is likely going to be the most true. May or may not work out all the time, but it's not a bad idea from a software development perspective. When faced with two possible ways of doing something, the more complicated one is the one your professor will most likely ask you to do. Sadly, that may be true in some cases. Not going to be true here. Simplicity is beautiful, and keep that in mind. And that kind of goes with keep it simple. So KISS, and we're leaving off the final S because we're not insulting anyone. Look before you leap. So that's where you basically want to check before trying to do things. So you essentially are avoiding exception. Sometimes it's easier to ask for forgiveness than permission. So EAFP, so you write code that performs an action directly. Basically it's deal with an exception block if things are not working well. That's closer to being more Pythonic than the LBYL. Like I said previously, you want to strike a balance between those two extremes. You want to probably not necessarily do a whole lot of looking before you're leaping, but you also don't want to be just always easier to get forgiveness and permission. Some resources that you may want to take a look at. And with that, I'll shift gears and talk about a separate topic for a little bit. And namely, let me get rid of this and do this. Why aren't I seeing you? Okay, we may have to do it the hard way. There we go. Hopefully that's coming across. Looks like it is. So this is kind of a bonus round where we'll talk about two things today. Free online and analytic environments. So this is kind of a brief survey of several of the ones. I may stop after Python. We'll see how things are going. I don't want to run too long on this. So kind of what's the point, right? A reasonable question. So we'll go ahead and jump straight in. Our agenda is what's the motivation, so we'll talk about why bother. Then we'll take a look at Google Colab and Databricks Community Edition for Python, RStudio.cloud, and Google's Colab R and Databricks for R, and then make some brief recommendations. So what's the point here, and what's the idea? So in your first deliverable, you were asked to set up a online or an analytics environment locally, right, on your desktop. Online versions of those kind of are already done, and there are what's known as a SaaS application. So that's a software as a service application. And that means that you basically don't have to do any infrastructure setup. You could just take your development environment with you, so to speak. You log on to something just like you do whenever you go to your Gmail account. You don't have to have a mail client installed and a mail server and all that stuff. You're just hitting a web page. Same basic concept. These are cloud computing paradigms that are surfaced through notebooks that you interact with through a web browser, very similar to what you do with Jupyter Notebooks locally. The reason you may want to use them is sometimes it's not practical to take your computer with you, especially if you have a ton of data and a few other things. And you may want to be able to do it from different endpoints, maybe a tablet, maybe a laptop, maybe a computer, possibly even your phone, but I don't know how that user experience would be. Sometimes you need more computational power than what you can get on your local computer, or you may not need it for as long. So you may need it briefly and then you want to let go of it. That's where elastic computing and the cloud comes to play. Sometimes it's just easier to do it online because you don't have to set up your own environment necessarily. Although for deliverable 1, no way around that one. You got to set up R and Python locally, but in Jupyter. Sometimes once you're past that and you're just needing to do some quick analytics, you may grab a file and pull it up into an environment and go to work on it quickly. What I'm going to talk about here are free, although some of them are like that freemium sort of thing where you get in the gate with it for free, but if you do too much or you need certain types of functionality, not so much free anymore, right? So you may want to keep that in mind. So talking about Python, the first one out the gate is Google Colab. I mentioned it briefly. So here's what it looks like when you open it up. And this is what it looks like whenever you get into it. That is a notebook itself. So you're looking at a notebook that is the intro notebook. So the notebook that you see when you first log in. And it basically gives you a basic idea of the equivalent of a hello world. So the cell there is showing you the number of days or seconds in a day and the number of seconds in the week, and showing that it is the interactive programming that we've been doing along the way. You can upload existing notebooks into this environment by going just to File, Upload, and then picking a notebook. And so you can pull in this case, a Titanic notebook that I've created locally, and it pulled it in without really any modifications. There's lots of different ways that you can upload to your data to these environments. This is one way of going through doing basically file upload. But you want to keep in mind with this approach especially, it goes away whenever your session ends, essentially whenever this virtual server that you're working on is decommissioned. You see if there says RAM and disk, that means you're basically running on a little container, essentially likely a Docker container. It's going to exist for some interval, after which it'll go away. That means that data that's associated with that essentially local virtual machine goes away when it's terminated. So simple to do, but only do that if for something that's kind of transient to nature that you're not going to want after the fact. You can also, once you've done that, you can access the file by using the name after you've uploaded it. You can also read files from URLs, probably the easiest way to do it. If you can get access to the data files, which you'll notice here, these are all from my GitHub account. So Alan at Rasmussen /data science data. And that's pretty much all of the data files that you need for this course in the datasets folder. So that what you can do here is do the pandas read CSV against a URL, which it supports natively, and that reads it into that data frame. You do have to do that. It's pulling it across, right, every time that is executed. But once you get it into that data frame, you can use that data frame going forward in various cells. So that's another approach. Another way you can do it, because we are talking about Google Colab here, right, is you can get it off of Google Drive. So this is a nice way that if you've already got your data up in Google Drive, that you can access it. A little bit of hunky or kind of funky things to go through here, where you have to do the files.upload, and then you choose a file, and then you read the io.bytes from the uploaded. Little counterintuitive, but it has that benefit that if the data is already on the drive and you want to just access it from your computer, that's one way to do this. You can also you can upload from your local drive via the code. So that's again using kind of this choose file sort of thing and reading it in. You can lastly mount your Google Drive if you're so inclined. And you can see here you have to go through a few sort of hurdles to get through it. You have to basically give Google Colab access to your Google Drive, and then eventually you'll be able to then to deal with it just as though it were a mounted drive, similar to what you mount inside of a Linux environment, likely because you're in a Linux environment under the covers. And then with this, we're basically, I granted it permissions. After it's done, I should be able to go back after I believe I get a magic token, although maybe not, maybe it just works. And then access it from the notebook. And we'll let this finish out. Yeah, so that's what I thought. You get a magic token, you copy that, take it back over to your notebook, and then paste it in. And that's basically a way of doing a variation of authentication, right? So you've got a code, you've now got access to it, and at this point you can actually access it with PyDrive, and you can take a look at, it does show up as a drive. So, and that is looking at your Google Drive from inside of Google Colab. So quite useful. It does have a little preview thing and so on. So do a quick live demo here, see how this goes. Okay, not control click, but just click. So again, the splash page, it does kind of load you with kind of some previous things that you've used in the past, some recent things, including things I might have dealt with in the past. Go ahead and open up the example of doing some deep learning using Keras, and doing a little bit of classification of items from images. So just to see this work, I'll go ahead and scroll down to some code and get it kicked off. So it knows that this is not Google's, somebody else's. I just did a shift enter. You can see up here it provisioned a little computer, a little virtual machine. This does have it looks like a GPU on the back end, which is kind of cool, especially given that this is free. And then basically here it just went through, downloaded the data that it needs. Then we can go through and do some visualization of the data. And it does pull back, I think that's a shirt. Then we do the typical data normalization, so that's basically getting everything into the same scale, so to speak. Doing a test train, oh no, that's doing a test train split as well. Or did that came, oh, it came in up here. So we are normalizing it, taking it down to a fraction of 255, and then we can see the test and train sets are split. There is some hover IntelliSense as well that keeps popping up. Then, and this is actually running against a GPU-based neural network on the back end. So this is a bit more computationally intensive than most of the things we'll do in this course. But the point here is that I didn't have to go out and get my GPU to work with this code. It just does. The reason that's relevant is sometimes that's hard to do. And in fact, right before this class, I was struggling to get my GPU to pass through to my Windows subsystem for Linux, something that would just make work, right? And so through here, we're doing some training. Probably don't want to wait while that runs. So we'll go ahead and switch back and move on to the next one. But the basic takeaways here, while that is before we leave, is it's a really nice environment, very easy to get up and running. It does allow for as much storage pretty much as you have on your Google Drive in a persistent fashion. Also, there's a certain amount it gives you kind of for free. You can see up here where it says the disk. Looks like they gave us 68.35 gigabytes, again, for free. And it is running reasonably quick doing its training, so that tells you that's not a wimpy GPU either. So pretty cool stuff. Moving back. Databricks Community Edition. So kind of a different thing. The Google Colab is very much around doing collaboration experimentation in notebooks. It does allow for people to work together, hence the name. And it is very much of a cloud hosted computation for what are essentially Jupyter notebooks or notebook sort of thing. Databricks is instead a cloud hosted version of Spark, basically. It is, that is the purpose of Databricks. The company was created by the founders or the creators, the original creators of the Spark framework. And so because of that, its intent is to teach you how to use Spark to some extent. It does support Python, R, SQL, and Scala. You can do things for free, but you are limited to a single node cluster. That means basically Spark itself is meant to be a distributed architecture with one driver and multiple worker nodes in a cluster. What the Community Edition is simply a single node with one, basically the worker and the driver are together on the same virtual machine, so to speak. Under the covers, you don't really care about it. You just say, I want some processing, and you get it. The challenge is from a data science, especially early in your journey, data science, is that it doesn't, I mean, you can use pandas, but it's kind of a little limited in nature. It's not really what it's intended to be done with. There is a similar data frame sort of package called Koalas that's pretty close to being pandas. It's not 100% the same, but it's pretty close. It does allow you to kind of do the same sort of work. Most of the Python libraries that you would use are available to you as well. The biggest challenge I've had using Databricks and trying to do it in a course like this is that if you do something like just use the Databricks upload capability of uploading a file, you have to go through some hoops to get it into pandas, right? And so that's kind of the downside. So we'll go ahead and see if we can take a look at that as well. We popped the wrong window, so I'm going to copy that, close that, and for fun, it did finish training, which is kind of interesting. 10 epochs through. So I'm switching identities here so that I'm running as Rasmussen. There we go. So this is what Databricks Community Edition looks like. I've been here before, so there's some additional things that finally came up. In particular, I've been doing some stuff with graph frames along the way, and some other stuff. The left nav, pretty straightforward. There is this concept of a workspace. A workspace is where your files are. It doesn't make as much sense whenever you're dealing with a Community Edition version of this. What they've done is taken their premium sort of offering, limited its capabilities, but still kind of a lot of the things are here, because if you're this environment, Community Edition doesn't allow for concurrent users. It's a single user environment. You can't really have two people collaborating very well. So because of that, some of these don't necessarily make sense. But you can see the basic, the navigation. I'm going down in here and I'm basically looking for the Titanic, just being able to load it. And this is R. So we'll see how this goes, because it supports R. Up here you can see which language the notebook is intended for. You basically can change languages in each cell inside of Databricks, which is kind of cool. You can see that you could switch the language, the default language for this notebook, if you were so inclined by picking a different one. If for some reason you want to do something like embed Python in the middle of this, you use a magic string of %Python, and then you can do just Python code, right? There is some trickiness of changing, like having data frames go across. You have to convert them into something called a temporary view for that to work. Also, you have to spin up a cluster to get this to work. You can see that it's saying that there's no cluster. Fortunately, if you go and try to run something, it'll say, do you want to create a cluster? And so I say yes, launch and run. And at this point, it goes out and it starts provisioning a cluster. It's not something you have to do yourself. It does it for you. But it's not as seamless as what you see in Google Colab, right? It's a bit more harder, for lack of a better word. You can also go over and see inside of Compute, because they are leveraging the same UI as the non-community edition, but you can only create a single cluster here. If I try to create more than one, it'll yell at me and say you can't do it in this environment. This is going through the process of creating a particular version of Scala and Spark. And when it's all said and done, you get a 15 gig memory with a couple cores in it. So reasonable amount of computation. It does automatically shut the cluster down after 2 hours of being idle, but there is no limit on how much you can use this. So it is kind of cool in that regard, nor is there a limit inside of Google Colab. It does support, as I mentioned, different languages, R, Python, SQL, and Scala, and it does so pretty much in a first-class way. You can also pull in libraries if you're so inclined to support you. In the case of R, you can go into CRAN and look for a particular CRAN package that you're interested in. If the work you were doing was more centered on Python, you go to PyPy, and Maven if you're doing something in Scala. So that's kind of it in a nutshell. You can also upload your own libraries as well onto the cluster, but given that these clusters are pretty much transient, they go away pretty much after you're done, not necessarily a great idea. So with that, we'll go ahead and switch back. And this is basically going through showing the same sort of thing. If you haven't logged in, or you log in just as I did, if you haven't signed up before, click and say sign up, say you want to try it, you give them your information, and then you get started. So you can go in, it's just as I'm doing here, and pick some company to be associated with, give it an email address, title, and then a phone number, or not, and then say just get started. And basically with that, all you have to do to get started and get an account. So pretty ease of entry. Again, their whole purpose here is to try to get people onto their paid editions of things, not necessarily just to be doing a good bit of free service here. So also looks like there's been a bump potentially in the amount of memory you get with time. So this is the dashboard we saw when we came in. So with that, we can take a look at R. Just talked about all the Python things. Unfortunately, there's only kind of a couple here. RStudio.cloud very much looks like R Studio, but there are some catches, right? Here's what the homepage looks like, but you get 15 project hours per month, so you could potentially run out of that pretty quickly, especially if you're using it into a class like this, and you might spend some time having to do some diagnostics. 15 hours is probably not all that long, really. Also, pretty wimpy amount of memory and CPU that you're getting. And you get 1 hour of background execution time. So that's pretty much it. Otherwise, once you go through that, then they start trying to get you to pay. So $5 a month for 50 project hours and so on, and additional hours at 20 cents per hour. So be cautious if you actually go this route and take a look at it, because it could get expensive quickly. What does it look like? Pretty much you go through the installation. So you want the free thing, go ahead and sign up. They try to sucker you into getting into the plus or the premium. Give it an email address, or you can sign up with your credentials of Google or whatever. Once it's through, pick your account. Pick a name. And then once you're inside of a workspace, you can create a project, and it goes through and deploys the project for you. You can give it a name. Once it deploys, you end up on something that looks an awful lot like RStudio. And in fact, almost impossible to tell the difference, right? I mean, there's probably some subtleties here and there that are different, but it's really difficult. Interestingly enough, in the non-free version of Databricks, you can actually install RStudio just like this as well. So it'll look pretty much identical. So whatever mechanism they're doing here is pretty common. So it is quite likely that you can do it. Here, if the point you try to do some import, it's going to make you install the things that are necessary so you can actually pull the data in. And it's actually doing the installation as this is going. So once it's there, we can say create an R script, and then potentially, just as you do with everything else, give it a name, then put whatever instructions you want inside of your R script, and it can do things like save on source or source on save and various other things as well, as you're used to seeing. Here's the typical code, the reading in the Titanic data set, and you can see pretty much just like what you do in RStudio. So really straightforward. Also, Google Colab does have a way of getting into R, but it is hackish. One way you can do it is to use the RPy2 package, but you have to put in %% at the start of every cell. A better way is you can actually create a runtime R runtime notebook, but you have to use this special sort of link every time. So collab.to/R, and it'll create an R notebook for you, but there's no way to do that through the UI. You have to use that link itself every time. So a little bit kind of an odd thing. Does get you inside of, once you do, the notebooks are very much similar to what you're used to seeing. And then the same sort of thing you can upload, and this basically is the same sort of concept. The way that we're doing it here, it's into essentially the file system of this temporary virtual machine. When the virtual machine goes away, the file goes away as well. There's also a potential of getting it from other places as well. And again, similar concept of adding cells, kind of cool, pretty easy to use. I like Colab, but it is, you do have to do some things like install your packages that you're likely going to want to use, require some libraries that you're going to want, and so on. And the fact that it's got a hidden URL is kind of annoying. You can create a graph as well, but you probably want to evaluate it on a line by itself or a cell by itself so that it'll display it correctly. Databricks Community Edition does also support R more in a first-class way. You basically just say that you want your default language to be R, just like the Titanic set I showed you a moment ago. And then this is pretty much the same sort of thing. And again, we're loading it in from a URL versus from the file system. It's a simpler way to do it with these sort of environments. Recommendation, it's up to you. RStudio Cloud is probably the best environment, but be cautious because you could easily exhaust your 15 hours very quickly. But it is identical pretty much to your RStudio. So that's one element to be considered with. If not that, then probably Databricks, because you don't have to go through any kind of special URLs to get there. You can just add and it works. The Python or the Colab, Google Colab, is not bad, but it's a little less mature in my mind. In Python, I would probably recommend Google Colab if you were going to do something online. It's really easy to use. You don't have to deal with the back end yourself. It just kind of magically happens. Highly integrated with the Google ecosystem, so it's pretty easy to get stuff off your drive if you have one. A backup to that would be Databricks as well, because it is very robust on Python. The reason that I would put Colab ahead of it is that you don't have to do some of the weirdness you have to do to get access to the data that you might inside of Databricks. So with that, here's some potential references that you may want to take a look at if you're so inclined. Also, those URLs there inside of my GitHub account are the Rossmann datasets that you might be needing, along with the Titanic and so on. And with that, I'll wrap this up. If you have any questions about the material I've talked about, let me know. That's what I'm here for. Stay safe, and we'll talk again on Thursday.